A 1.0 meter long, 1.0 millimeter diameter nichrome heater wire is connected to a 12-volt battery. What is the magnetic field strength 1 centimeter away from the wire? The resistivity of nichrome is 108 times 10 to the minus 8 ohm meters. So in this problem, we're dealing with an actual circuit. We're dealing with a wire whose purpose is to heat something up. This is a nichrome heater wire. And this wire has a large resistivity. And you know, with the large resistivity means that the wire will have a fairly large resistance. And it is the resistance in the wire that dissipates electrical energy in the form of heat. So our goal is to figure out what the magnetic field strength is a certain distance away from this wire. And in order to do that, we're probably going to need to know something about the current that passes through this wire. So to begin our solution, we're going to start with a sketch. Here is our 12-volt power supply. The EMF is equal to 12 volts. This power supply is attached to a nichrome wire. Now, since this nichrome wire has a resistivity of 108 times 10 to the minus 8 ohm meters, we are going to model this wire as a resistor. So here is the resistor representing our nichrome wire. Being a resistor, we know that it's going to have a certain resistance based off of the geometry of the wire. So let's go ahead and look at that. If this is representing our wire is of length L. L is 1.0 meters. Our wire has a diameter that is 1.0 millimeters. Now, of course, this is not to scale. Using this information will allow us to determine the resistance of this wire. Now, why do we need the resistance? It's because we need to know the magnetic field a certain distance away from this wire. And we know that magnetic fields are generated by moving charge. Since this wire is attached to a battery, a current I flows through it. We don't know what this current I is, but this current I is going to be the source of the moving charges that will generate the magnetic field at a certain distance away from the wire. And we know from a previous derivation that the magnetic field due to a long, straight, current-carrying wire is equal to mu naught I over 2 pi r, where I is the current in the wire, r is the distance away from the wire, and the direction of the magnetic field is given by the right-hand rule. So this is our goal, to find the magnetic field at a certain distance r away. So let's go ahead and do another sketch of the wire so we can put our information in better context. We will say that the wire lies along the positive x-axis, and the y-axis is vertical, the z-axis is coming straight towards us out of the screen. We want to find the magnetic field a distance of r away from the wire. And we know the magnetic field from the right-hand rule forms concentric circles about this wire. The direction of the orientation of these concentric circles given by the right-hand rule. And from that, we know that at this point that I've drawn for the point to evaluate the magnetic field will be tangent to that circle that surrounds or is centered about the wire. Now, this wire carries a current I, and that current I is the source of the magnetic field at the point at the distance r away from the wire. So our goal is to figure out that current I. Now, in order to figure out the current I, we're going to have to turn to our experience with circuit analysis. When we look at this sketch of the circuit we've drawn, let's identify two nodes, A and B. We can use Kirchhoff's law for voltage to say when we sum the voltages in a complete loop, starting at point A and ending at point A, that is just the sum of the voltages of each of our components in the loop, and that sum must be equal to 0. Now, from this, we know that the voltage from A to B is given by the EMF of the battery. We know that the voltage from B to A is given by the potential difference across the nichrome wire. And we're modeling the nichrome wire as a resistor. So this would be the potential difference across that resistor, which is equal to minus the product of the current times the resistance. And this is equal to 0. Now, what this expression allows us to do is it allows us to get a relationship between the current, the EMF of our battery, and the resistance of the nichrome wire. So we now have the current, which is a key part of the formula for finding the magnetic field a distance r away from the wire. Now we have to find the resistance of the wire. We know for a conducting wire, resistance is given as the resistivity times the length of the wire over the cross-sectional area. Well, remember, our wire, we are given the length, L, we're given the diameter, D, and we're given the resistivity, rho. That diameter, D, allows us to find the cross-sectional area being the area of a circle. So the area of a circle, remember, is equal to pi times the diameter squared over 4. Well, you're probably more used to saying pi r squared. Well, remember, the radius is equal to the diameter divided by 2. This means the resistivity is given by the resistance is given by the product of the resistivity and the length divided by the cross-sectional area, which is pi d squared over 4. So we now have an expression for the resistance being equal to 4 times the resistivity over pi times the diameter squared. Since we now know the resistivity, we could plug the resistivity into the current. Remember, the current is equal to the ratio of the potential difference divided by the resistance. So this is equal to the EMF of the battery over 4 times the resistivity times the length of the wire over pi times the diameter squared, or the current is equal to pi times the EMF of the battery times the diameter squared over 4 times the resistivity of the wire times the length of the wire. Now we have all the pieces we need to find the magnetic field at a distance r away from the wire. So the strength of the magnetic field is given by its magnitude, which is equal to mu naught times the current in the wire over 2 pi times the distance away from the wire. So this is equivalent to mu naught over 2 pi r times the current. And the current is given as pi, the EMF of the battery, the diameter squared of the wire, over 4 times the resistivity of the wire times the length of the wire. And this is just pi, permeability of free space, mu naught, the EMF of the wire, the diameter squared of the wire, over 8. Well, let's go ahead and cancel that pi, since we have a pi in the numerator and the pi in the denominator. Can get rid of that pi. And we are left in the denominator 8 times the resistivity times the length. So plugging in numbers, we have the magnetic field is equal to the permeability of free space, which is given as 4 pi times 10 to the minus 7 Tesla meters per amp, times the EMF of the power supply, which is 12 volts, times the diameter of the wire, which is 1.0 millimeters, and this is squared, divided by 8 times, oh, I see here that I forgot to write down my R. So that R is the distance away from the wire. So that distance away from the wire is 1.0 centimeters times the resistivity of the wire, which is 108 times 10 to the minus 8 ohm meters, times the length of the wire, which is 1.0 meters. I see a meter cubed in the numerator, cancels with a meter cubed in the denominator. Remember, a volt per amp is the same thing as an ohm, so that those cancel, leaving us with units of the Tesla, which is what we are looking for. When I plug this into my calculator, I get 1.7 times 10 to the minus 6 Teslas, or we could just say 1.7 microteslas for the strength of the magnetic field due to this nichrome wire carrying a current at a distance of 1 centimeter away from the wire.